for step 8. So what we do here is now we're just going to change up some of the initial values of that we have in our system. And so in our program, we have a deuteron. So we have it's a proton with a neutron on it. So its elementary charge is just 1 with a mass of 2. And so now we're going to ask the question of what happens when it's just a proton, right? It doesn't have a neutron with it. So it just has a mass of 1. You know, we can begin to think, well, having the mass be smaller, will that lead to a larger gyro radius, or will it lead to a smaller one than what we saw with the deuteron? So we go back to our code. So this is what we got with the deuteron. We got this result. It's a mass of 2, and it created this gyro radius right here. So now we change our mass to 1, because now it's just a proton. And let's see what happens when we run it. So our proton enters this electric field. Boom, and you saw it has a tighter, a smaller gyro radius here. So what's happening is that we cut the mass in half, essentially, and thus the force in the electric field is the same, but there's less mass. Now it's 1 instead of 2, so that must mean our acceleration has to be twice as large, or needs to be larger, and thus it accelerates our particle more, giving a higher velocity. However, when we enter the magnetic field, now the force of the magnetic field can easily act onto our particle because it's lighter, thus deflecting it easier, and thus leading to a tighter gyro radius. So pretty neat. You're welcome to just change this mass to other values to see what happens, but we'll go ahead and go on to the next step. And so for this next step here, we're going to change the charge of our particle from positive to negative, and we're also going to change the electric field from positive to negative, just to see if the particle moves in the way that we would expect. Make sure to change these functions to represent positive to negative. Then as well, our variable q, make sure from 1 it goes to negative 1, and for the defined electric field we switch it from positive to a negative 1, and we can see what happens. So here I'll go back into our program, and here is our charge. Let's make that -1, and where electric field was 5, so now let's make it negative, and then you scroll down and make sure this is negative. And now we'll run this, and let's find out what happens. Oh, nice. So now our particle, given a negative charge but also given a negative electric field, it goes down. So a way to think about what's going on here, what's different, we could go back to our right hand rule, and the whole same logic applies, right? So we have this negatively charged particle coming in like this way, and we have the magnetic field coming into the page. So that's our that's our V cross B value, and so that value is positive. But then we need to account for the Q, because it's Q times V cross B, and now it's a negative, and so we would expect it now to go down, and that's what occurs here in the system that you've designed. So, by the way, you might be wondering, we kept the mass the same, right? It's still 1, but now the charge is -1 instead of +1. So what this can represent is a hydrogen ion. It's a particle that has a abundance amount around the sun, and it's a particle that has a proton but 2 electrons. And electrons, their mass is really tiny. The main mass comes from that of the proton, and thus this is something that can exist, and this could be a depiction of that here. And then another claim that we make is that the speed shouldn't be changing at all. And so while we're saying that your simulation or our simulation says different. All right, so we go back into our program and let's just run it and see again what is going on. And so we have our positively charged particle come in, gets accelerated, has some velocity when it comes out, and then at the end, right before the program ends, it has a measured velocity in the x direction of 42.9 and a final velocity in the y direction of 1.7. And so we're saying that the speed doesn't change, right? And just to emphasize that it did change for our program, we're going to go back and we're going to turn the magnetic field off and just saw what the velocity should have been given only this electric field. So we go to our program and let's just get rid of this magnetic field here and play it. You see our magnetic field's disappeared and now it acts on this electric field and boom. And so it has a final velocity in the x direction of 40. Thus this means it has a speed of 40. And so as a sanity check, we're going to calculate the speed of when we had the magnetic field and compare that to the speed that we got here. Because we're telling you there shouldn't be a speed change at all, and so we just want to see how much error there was or how much difference there was between the two speeds. And so just to get our numbers back, this is of the same simulation. It's just so the solutions that we shared with you in the exercise. And so here, so we have to get the speed from a velocity, you just squared each speed in each direction, and then you square root that summation. And so let's write, square root sign, and then it was minus 42.9, and we square it, plus, and it was 1.7 square, and that gives us 42.93. And so this is what we observed. And I'm telling you that speed isn't changing, and it should be that of what we saw when we turned the magnetic field off, and we should expect a speed of, the velocity is 40, but if there's only speed in x direction, so you square it, square root it, so it comes out to the same thing. Speed's 40. We will be using the glass board after this to kind of define it more and work through it a little bit better to see it, but the true value should be that 40. And so to get what the error is, you do 40, which is the true value, minus that of, let's just get copy paste, and then divide that over 40, and then this is just the amount of error. To get percentage error, you can multiply that by 100. Later we say that when accepted value is between plus or minus 10%, and here we get about 7.33%, which is all right. That just means that, something we want to keep emphasizing is that our program to depict the physics that's going on, what's being acted onto our particle, it's being off by about 7%. So it's not great, but there are ways to make it better, to make that as close to zero. The closer to zero, the better. It's representative of the physics that's actually going on. And I work with programs and codes that do that by including a little bit more complex math, but it does still run at a relatively fast speed as our program did. But that's outside the scope of this exercise, but just know that there are methods out there that can make this error be smaller and be more accurate and true to the physics actually going on.